Assalamualaikum and hi to Sir Samsul. Today we will present our project for digital electronic, the up and down 10 counter. This project was done by Syafiqah Zulaika, Syaidatul Fahana and Nurul Syafinas. What is up and down modes 10 counter? A mode 10 counter count for 0 to 9. This is resets back to 0. This is called mode 10 because there are 10 stages total. Up and down counter can count the both direction, up or down. The direction is controlled by signal C. If C 1 is count up, if C 0 is count down. So we use 4 JK flip-flop. That means Q3, Q2, Q1, Q0. JK flip-flop are used because they are good for counting and toggling. We also use logic gates and control input for direction. When do we use the counter? It is used in digital clocks for second and minutes, timer, scoreboard. So now I will present about truth table for our up and down mode 10 counter. This is count for output bits Q3, Q2, Q1, Q0. This output represent the current number in binary from 0000, which is 0, up to 1001, which is 9. Since this is a mode 10 counter, it's only count for 0 to 9. After 9, it goes back to 0 when counting up. And if counting down, it goes for 0 back to 9. The counter input, which we label as C, decide the direction of the count. When C is 1, the counter will be count up. When C is 0, the counter will be count down. So for every clock pulse, the output is increased or decreased based on the value of C. So for example, if C 1 and the current output is 0001, which is 1, the next output will be 0010, which is 2. But if C is 0 and the current output is 0010, which is 2, the next will be 0001, which is 1. The truth table shows all possible stages of the counter and how it's changed based on the input counter. It helps you understand and design the logic needed for circuit to function correctly in both counting direction. Now, I will explain the Karnaugh map or K map for the JK flip-flop. Our counter will use JK flip-flop because they are suitable for toggling operation, which are perfect for counting circuit. Each flip-flop Q0, Q1, Q2, Q3 has a key match for simplify the logic. We use the present stage and next stage for each output will to fill the key match. For that, we determine the value for J and K needed to make the flip-flop works correctly. The K-mat help you find the simple Boolean logic for each input, so we can reduce the number of gates used in the final circuit. So basically, this step is important because it allows you to design the more efficient and simple counter. For the K-mat, we get the Boolean expression for each J and K input of the flip-flop. Each JK input has its own logic equation based on the simplified value for the K-mat. For example, the input J0 and K0 may always be 1 because Q0 toggle every clock pulse. For G1, K1 and the rest, the logic depends on the states of our flip-flop and the control input C. These Boolean expressions are then used to design the actual circuit using logic gates like AND, OR, and NOT. By using the expression, we can connect the flip-flop correctly to build the up and down mode counter and make sure it works as expected. Now, I will explain all the components used in the circuit, include the power supply and how each part works together to make the up and down mode 10 counter functions. So the circuit, the power supply. The circuit use a DC power supply, usually 10 volt standard for TTL logic. This power is connected to all logic IC and flip-flop to make sure they works properly. The ground is also connected to complete the circuit. So first two, JK flip-flop have a 4 unit. We use 4 JK flip-flop which labels as a Q1, as a Q0, Q1, Q2, Q3. Each flip-flop store 1 bit of the binary count. So together 4 flip-flop can count from 0, 0, 0, 0 to 1, 1, 1, 1. Basically 0 to 15. But we limit it to 0, 0, 0, 0 to 1, 0, 0, 1, 0 to 9 for mode 10. JK flip-flop have J and K input for control whether to toggle or hold clock, trigger the change, Q output for current stage, reset for clear output to 0. We have 3 logic gates: if AND gate and OR gate and NOT gate inverter. For AND gate, used to combine signal Q output and control signal C. For OR gate, used when we need to allow the each of 2 input to active a function. NOT gate is inverter. Inverter used to reverse logic. When C is 0, we use not C to get 1. These keys are used to generate the correct logic for each J and K input depends on the current stage and the count direction. Clock input. Clock input is sent to all flip-flops on every rising and falling edge of the clock depends on flip-flop type. The output may change state. The clock keep the counter moving step by step. Control input. It is a manual switch or logic level input that determine the counting direction. C is 1, count up. C is 0, count down. Is connection. The logic circuit for that is counter to behavior of the flip-flop input. Reset logic or limit logic. Since the counter is a mode 10, it must go for 1001 back to 0000 when counting up. For 0000 back to 1001 when counting down. This is done by adding logic that detect when the count reach 9 or 0 and send the reset or preset signal. Output display. Output display is option. Is some design. The Q output Q0 to Q3 can be connected to LED to show the binary value, or 7-segment display with binary to determine decoder. This helps visualize the count in the real time. So now we can see how the circuit, that simulation. So they count 0 to 1, 8 to 9, then reverse back to 0 again. In conclusion, the project has really helped users understand how mode 10 up and down counter works. We learned how to use JK flip-flop logic gates and control signal to build the working secret. We also practiced creating truth table, Carnot map, and Boolean expression to simplify our logic. This project improved our skill in digital circuit design and made us more confident in analyzing and building sequence circuit. More importantly, we saw how the kind of a counter is useful in real-life systems like digital clock, timers, and scoreboard. Thank you.